A basis of a vector space makes it possible to represent any element of that vector space as a sequence of numbers. And of course, a different basis of the vector space would require us to use a different sequence of numbers to represent the same element. Now, if we have a basis B, let's say the elements are v1 through vn, of a vector space V, and an element that is a vector in the space, little v, which is equal to, let's say, a1v1 plus a2v2, etc., up to an vn. The a's are scalars. Then we can represent the element say in a computer by just the numbers a1 through an, maybe written as a column vector. We call this the coordinate vector, or component vector in the book. Of V with respect to the basis B. In the book, this is written V with square brackets around it, sub B equals a1 through an. This notation means the coordinate vector of V with respect to the basis B. For example, let's let V be polynomials in X of degree less than or equal to 3. Let B be the natural basis 1x, x squared, x cubed. Every polynomial of degree at most 3 can be written as a linear combination of these powers of x. Now the element 1 minus 3x squared plus 8x cubed let me call this p of x so the polynomial has a name. It has coordinate vector 1, 0, negative 3, 8. With respect to, I'm going to write WRT a lot, with respect to B. So thus in the notation, P of x inside of square brackets sub B equals 1, 0, negative 3, 8. Now if someone else lists the basis in a different order, let's say greatest power first. So x cubed, x squared, x1. And let's call this basis b prime. Basically the same basis, but written in a different order. And the coordinate vector becomes, so first we list the coefficient of x cubed, which is 8, and then the coefficient of x squared, which is -3, and the coefficient of x, which is 0, and then the coefficient of 1, which is 1. So we could say p of x square bracket b prime equals 8, -3, 0, 1. So I guess if we're representing an element of a vector space by coordinates, just by numbers, we have to decide on an order of our basis, because the first coefficient is supposed to represent the coefficient or multiple of the first element of the basis. The second coefficient corresponds to the second element of the basis, and that's different if we come up with a different order for the basis. Now usually curly brackets in math mean to ignore order. And parentheses mean to remember order. So it would be good if we could remember to put parentheses in our bases. I don't dare. These are supposed to be curly braces. On the other hand, most people use curly braces, and they mean remember order, which is a slight abuse of the notation. But I'm going to try to write parentheses because it would be more correct. So parentheses are more correct for bases, but honestly most people write curly braces. All right, now let me come up with another basis, which isn't just a reordering of the first basis. It'll be a genuinely different basis. So another basis of V, polynomials of degree less than or equal to 3, is, let me put parentheses here to practice what I'm preaching, 1 plus x, 1 plus x plus x squared, 1 plus x plus x squared plus x cubed. And let's call this C. This is a new basis, capital C. So a natural question is, what is the coordinate vector of the polynomial with respect to this basis? Again, the polynomial is 1 minus 3x squared plus 8x cubed with respect to the basis C. Well, to answer this question, we have to solve some equations. So we'll solve some multiple of 1 plus some multiple of 1 plus x plus some multiple of 1 plus x squared plus some multiple of 1 plus x squared plus x cubed equals 1 minus 3x squared plus 8x cubed. Now, two polynomials are equal if the coefficients of each power of x are equal. So the constant terms on both sides have to be the same. The coefficient of x on both sides has to be the same. The coefficient of x squared on both sides has to be the same, etc. So we're going to equate coefficients of powers of x on both sides. So the constant term says that, let's see, C0 plus C1 plus C2 plus C3 on the left equals 1 on the right. And then coefficient of x is C1 plus C2 plus C3 is the coefficient of x on the left, equals 0 because there's no x on the right. And then the coefficient of x squared on the left is C2 plus C3. And on the right, it's negative 3. And then the coefficient of x cubed on the left, there's only an x cubed here. So C3 equals 8. Now this is a triangular system, so we can solve one variable at a time, and then each preceding equation just gives us one more variable, so this is pretty easy to solve. So we have C3 equals 8 according to the last equation, and then C2 plus C3 equals negative 3 implies that C2 equals negative 3 minus C3 minus 8, which is negative 11. And then C1 plus C2 plus C3 equals 0 tells us that C1 equals 0 minus C2 minus C3, which is, let's see, minus C2 is plus 11, minus C3 is minus 8, so that's 3. And then C0 plus C1 plus C2 plus C3 being equal to 1 tells us that C0 equals 1 minus C1 minus C2 minus C3. Which is 1 minus C1 is 3. C2 is negative 11. Minus negative 11 is plus 11. Minus C3 is minus 8. So we've got 1 minus 11 plus 11, so that's just 1. So that means that the coordinate vector of P of x with respect to C is, so C0 is the first one, 1, 3, negative 11, 8. The end.